Let's go through and actually do a proof of the correctness of the naive algorithm we just spoke about. So I'm going to proceed by taking advantage of a particular observation. So what we're trying to prove here is the correctness of the claim that naive AB outputs the product of A and B. So the observation that I'm going to make is that before or after the while loop in the implementation of naive, this statement is always true, that the variables x and y multiplied together and added to z is exactly equal to a times b. So how are we going to show that this is the case? So the first time we're going through the while loop, in the very beginning, at the top of the function, x is assigned to a, y is assigned to b, and z is assigned to 0. So let's check the expression with those variables plugged in. We're saying that's a, b equals a, b plus 0. Well, that's kind of obvious. The next thing we're going to show is that if it's the case that at the beginning of the while loop, this condition holds that a times b is exactly equal to x times y plus z, then it's going to be the case that with the new values, so x, y, and z may change, the new values x prime, y prime, and z prime are going to satisfy this as well. So if it was true before, then it has to be true after. So why would this be true? Let's remind ourselves what the code looks like again. So what happens in each iteration of the loop is that a new value of z is computed, which is the old value plus the value of y, and a new value of x is computed, which is the old value minus 1. We basically have the new value of x is the old value minus 1, the new value of y, well, it didn't change, and the new value of z is the old value of z plus y. All right, so now what can we say about x prime times y prime plus z prime? We know what x prime, y prime, and z prime are, so let's substitute those in. That's x minus 1 times y plus z plus y. And now we'll just do a little bit of algebra. Multiplying this out, we get xy minus y plus z plus y. And these y's, plus y and minus y, cancel, and so we get is xy plus z. But notice what we assumed. We said if it was the case that xy plus z is equal to ab, then what we're showing is that x prime, y prime plus z prime is equal to ab. Well, guess what? We showed that x prime times y prime plus z prime does indeed equal ab if it was true at the top of the loop. So this condition that we're testing here, this ab equals xy plus z, is maintained through each step of the while loop. It starts out true and it remains true each time it goes through the while loop. So what we know is that while this code is running, each time we go through the while loop, this condition is always true. And eventually the while loop terminates. The while loop terminates when x equals 0. So what does that mean? xy plus z has to equal ab, but x is 0, so that's 0 times y plus z equals ab. This has to be true. Well, 0 times y is 0, so this is actually saying that z has to be equal to ab at the end of the loop. Once x reaches 0, z has to equal ab. Keep in mind, that's exactly what we return, the value of z. So the thing that is returned is going to be a times b. So let's just take a look at the code again and see that that's what it's doing. Each time it goes through, it's decrementing x, accumulating the values in z, and eventually when x is exhausted, it returns z, and it is exactly a times b.